Hey, this is Horner, and this is your first lecture notes. This is on chapter one, and all I really like to do here is just kind of highlight some of the things that I think are really important in the first chapter. I'll do this for each one of the chapters that we do, so if you like lecture and you like kind of going through and kind of watching me just go through the notes and trying to explain things, that should be helpful for you. You can fast forward through this, you can rewind, however you want to do it is absolutely fine. Um, if you're not a lecture person, then this might not be as useful, but we're just trying to hit everybody at their different learning styles. Class is going to be really important. You want to make sure you're there and actively engaged, and that will help kind of go back and reinforce a lot of things that you're going to see in these lectures. This is just my version of GM Batista. That's your book. It's a really great book, written at a really great level so that you'll get everything out of it that you need. Question is, why study physics? And it's mainly because physics is kind of the root of all the other sciences. It can describe matter, energy, space, time, and everything else at a really fundamental level. So if we think about physics at the smallest level, that actually helps us understand a lot of the different forces that we see around us, as well as look at how the atom is structured. So if you know how the atom is structured, then you can go into chemistry. Chemistry then goes on and helps us explain a lot of the things that are happening in biology and biochem. For any field of study really that you're trying to plan to do, whether it be biology, architecture, medicine, almost anything. A lot of you I know are physical therapy students. Then this is going to be a great little class for you to really help you understand your field a little bit better. I know I had a lot of students last semester that used a lot of what we did when they went on some of their internships and things, and were able to kind of look at how physics affects the human body, especially those physical therapy students. Physics is in biology a ton. And you'll see that in the Physics 160 that University of Indianapolis offers, that goes into a lot of the electricity and magnetism and really kind of shows you how there's that interaction between even within a cell. So you talk about how ions move across channels and things. A lot of that has to do with physics as well as chemistry. So we're really going to try to make sure that we tie physics to your field of study, whatever you're doing, no matter whether that's in science or not. But most of you, I think, are probably going to be in this area here. We're going to look for patterns in physical phenomena that occur in the universe. We're going to try to explain why things happen. But one of the biggest things that I like to do is make sure we change any misconceptions that you have, because if we can change and make sure that you understand things in the correct fashion, that will make everything else a lot easier as you go through your other studies and your study of physics in itself. Um, if we talk about physics and we can just say, you know, what does physics do? It'll help us provide a distinction between similar terms. For example, speed is basically just how fast you're going. So you might say that you're going 55 miles per hour. But if you're on the highway and somebody wants to know where you're going and you say I'm going 55 miles per hour, that's not going to tell them much. So velocity includes the speed plus a direction. So I might say I'm going towards Michigan, so I'd be going 55 miles per hour north. Mass and weight do the same type of thing, but in terms of just trying to find a distinction between the two. Mass is actually measured in kilograms. And weight is different. Weight includes the force due to gravity, and so we would measure weight in newtons. They have totally different units, as you see here. And even though they are related, they're related by something that we all commonly see as gravity. So without gravity, you'd have trouble going through and really talking about weight, but you could talk about mass. So we'll deal with this in the first unit so you can really get into what the difference is between the two. But one of the things that I love about physics and taking a physics course is it'll help you correct your preconceived ideas that are incorrect. For example, a lot of people think that when you see the shadow on the moon, so for example, let's say that this much of the moon is in a shadow, a lot of people will tell you it's because the Earth, so here we're just going to put the Earth, is blocking light going to the moon from the sun. So if we have the sun here, So that's my best sun, and the light's going through and it gets blocked and then hits the moon. That's the phases of the moon. That's what a lot of people say, and actually that's not true at all. The only time that you have the Earth in between the sun and the moon and you get that shadow is during a lunar eclipse. So we'll go through and try to really help you make sure that your ideas in physics are solid, and that'll translate into solid physics, which means that you'll have some really good experiences in chemistry, biology, and some other things that you'll do. We will use math a lot in this course, of course, and we're going to look at numbers, and we know that numbers always need quantities. If I ask you to measure something and you tell me that the recipe calls for 5, I really don't know what you're talking about. If I'm asking you to measure a distance and you say 5, I'm not really sure what you're talking about until you put on a quantity. So if I'm talking about the distance from my house to my friend's house, I could say that's 5 kilometers. If I talk about the distance or the length of my finger, that would be 5 centimeters. So be very careful whenever you use numbers, especially when you're doing problems, because if you just put 100.1 and there's no unit there, I don't know really what that 100.1 means. It's meaningless at that point. Factoring, or just looking at factors, if I increase by a factor of 2, I might talk about the power emitted by a radio transmitter and I say that it's doubled. So we will deal with factors. We'll also say that maybe we've decreased something by a factor of 2. So you might be talking about the concentration of sodium ions in the bloodstream, and you'd say that it's about half of what it was previously. So we're decreasing by a factor of 2. So a lot of the skills that you'll learn just mathematically in physics will translate into a lot of other subjects and help you with those. In terms of percentages, if a quantity increases in percent, that's really the same thing as saying that we multiply it by a factor of 1 plus whatever that percent is divided by 100. So if we increase by 5%, you can just take 1.05 times the original value. So if you're increasing the price of a loaf of bread by 5% and it's $1, it'd be $1.05, because all we did there is we just took our number and plugged it into our fun little formula here, and that gave us 1.05 times the original value. If a quantity decreases in percent, we're going to do the same thing, but this time we're going to subtract off that percent. So decreasing 4% will give us 0.96 times that original value. So just some easy ways of looking at percentages either increasing or decreasing a value. Proportions, physicists will use a lot of proportions. We're going to do a lot with proportions in that first couple of classes, just so that you can think in proportions. We don't always have to multiply everything and get an exact number. We can kind of get a roundabout number by using proportions. For example, if we say that A is proportional to B, we would write A, and then this kind of looks like a fish, so we'll just say that's the proportionality sign. If A is proportional to B, we mean that if B increases by a factor, then A should also increase by that factor. So in other words, if I have a ratio of 2 values B, so I have B2 over B1, that's going to be equal to the ratio of the corresponding values of A. So my A2 over A1 would be about the same proportion. As a good example, you could think about maybe if I had 100 over 50, that would be proportional to 2 over 1. Essentially, you're going to get the same thing. You're going to get 2 in either case. So that one's going to be 2 and this one's going to be 2, but we're looking at how these ratios will match up and just look at them as proportions themselves. For the next part, we're just going to talk about using math and looking at a proportion for the circumference of a circle. You know that the circumference of a circle is just going to be 2 times pi times r, so all the way around would be 2 pi, and then we can multiply that times the radius of that circle. So if I increase the radius, we just say that if the radius doubles, then that circumference would also double, because we know that the circumference is proportional to the radius. So if I double the radius, I also double the circumference. If I want to know exact value, then I'd have to multiply that new radius times 2 times pi. But if I know the old radius and I know the old circumference, if I multiply the radius by 2, I would double that circumference. So The area, you could also think about the area of a circle, but now your equation is area is equal to pi r squared. So now my area is proportional to the radius squared. Here pi is a constant, so we don't have to worry about it because it won't change. And now that's not equal anymore. Instead, it's just a proportion. So if we can say that the area must increase by the same factor as the radius squared. So if the radius doubles, so if I double the radius, notice that the area would go up by a factor of 4. So if I write as a proportion, I could write a2 over a1 is equal to the second radius over the first radius, and then that number is squared. So that would be 2 squared, which is equal to 4. This is your first example, and this one's in the book. This is talking about osteoporosis, so trying to link medicine here, maybe physical therapy, biology to physics, and just some of the math things that we need to know. Severe osteoporosis here can cause the density of bone to decrease as much as 40%. So they want to know what is the bone density of this degraded bone if the density of a healthy bone is about 1.5 grams per cubic centimeter. So our strategy here, we know that n percent decrease means that I'm going to take 1 minus that n over 100. So I'm going to take 1.5 grams per cubic centimeter. I'm going to multiply that by 1 minus, and then we've got 40 over 100 is that 40%. So now we'll have 1.5 grams per cubic centimeter times 0.6, and we see that that new bone density is about 0.9 grams per centimeter. Here our final density is a bit more than half of the original density, and so that is expected for our 40% decrease. So quick checks really just say, hey, you know what? This number should have gone down. It should have gone down by almost half. When we look at our new number, it has gone down by that. So that makes it a little bit easier to kind of see what we're doing. That is example 1.1. For example 1.2, this says the effect of increasing radius in the volume of a sphere. They give you the volume of a sphere equation. It's just 4/3 pi r cubed, where v is volume, r is the radius, pi is a constant. So I've got a basketball that has a radius of 12.4 centimeters and a tennis ball has a radius of 3.2. They want to know by what factor will the volume of the basketball be larger than the volume of the tennis ball. So to do this one, it gives a couple of different radii, and those radii for the two balls. If we want to keep track of which ball's radius we're talking about, we're going to use B for basketball in a subscript. So you'll see that right here. We've got B as a subscript, and the radius of the tennis ball is going to use a T. Since 4/3 and pi are constants, we can work in terms of proportions. So we just know that the radius of the basketball is related to the radius of the tennis ball. By just dividing the two, we now see that the factor here is about 3.875. The volume of the sphere, based on our equation, is V is not equal to, but proportional to the radius cubed. So since that basketball radius is larger by a factor of 3.875, and the volume is proportional to the cube of the new radius, the new volume should be bigger by a factor of about 3.875 cubed, which is pretty close to about 58.2. So that's a little bit more in-depth example of how you can use proportions to solve some problems. Scientific notation, this is a pretty easy thing to do. We have in the scientific notation, any number can be written as a number between 1 and 10 times an integer power of 10. So here we've got the radius of the Earth, which is about 6,380,000 meters at the equator. And to clean that up so I don't have to write all these zeros, I'm going to start here and then I'm just going to move back, and you'll notice that you're going to go backwards 6 places. When I do that, I can now take my 6.38 and raise it to the power of 6 times 10 to the 6th. So this is a much easier number to recognize and to write than having the 6.380000. On the other end of the spectrum, here we've got the radius of a hydrogen atom. So now we're moving that decimal place to the right. When you move it to the right, your scientific notation now will be negative. So I moved it over 11 places, and I write it in standard form as 5.3 times 10 to the negative 11th meters. This really just eliminates the need to write the zeros to locate that decimal point correctly. And that's scientific notation. Significant figures, your data is really only as good as your measurements. If I measure the distance from my house to you, Indy, it's measured a lot differently than the length of a bacteria. So if you measure the length of a bacterium to the nearest kilometer, that would really be useless. It wouldn't help us much. So we'd really want to do maybe micrometers for it. Using significant figures, this is really important in physics, but it's much more important in chemistry. So there's a little bit of leeway when you do this in physics, and typically no leeway at all when you do this in chemistry. Some rules for identifying the significant figures. These are in your book. I'll let you just kind of read through these. If you want to pause the video, you sure can do that, but I'm not going to go through and read these to you. But I am going to help you a little bit with these 4 examples. So it says for each of the values, identify the number of significant figures and then rewrite this in standard scientific notation. So for this number, the 0 that I have here is what we call a captured 0. If I would take that 0 out, if I would scratch it out, that'd make this number 49.8, and that is nowhere near our number 409.8. So that 0 is very important, and so we're going to call it significant. Non-zero numbers are also significant, so the 4 is significant. We said the 0 is, the 9, and the 8, and the decimal point just holds the place there. So this one has 4 significant figures. If I want to write it in standard scientific notation, this would be 4.098, and I'm going to take that times 10 to the second. Notice that I've moved my decimal place over 2 places. This is our next number. The zeros here that are leading zeros are not significant. They're just placeholders. And I'm going to show you why here in just a second. But my trailing zeros mean that I've measured all the way out to these positions. So they are important and significant. These are not important. These are important because they kind of hold a place, but they're not significant in the front. Let's go ahead and write this in standard scientific notation. That'll help us determine how many sig figs we have. We're going to move this over 2 places so that I have one number to the left of the decimal point. And I'm going to put 8, 7, and then I'm going to add these zeros because they are significant. They are trailing zeros after the decimal point if you look at the rules. And this is times 10. And remember, we went to the right, so this would be -2. I forgot my unit there, so I'm going to put it on that one. Come back down. This would be centimeters. Now that I've written it in scientific notation, standard scientific notation, I'm going to count how many numbers I have here. 1, 2, 3, 4, 5. So this one actually has 5 significant figures. We don't worry about the times 10 to the -2. This number is a little bit different. I do have trailing zeros, but they're not after the decimal, so they're really just placeholders. They are important, but they are not significant, so I'm just going to X them like that. So this one really has 2 significant figures. Okay, there are 4 numbers that are important, but only 2 are significant. So I'll say that again. There are 4 numbers that are important because 9,500 grams is much different than 95. So I want that 9,500, so there are 4 important numbers, but only 2 significant numbers. If I write this in scientific notation, it'd be 9.5. Notice I'm not going to put the zeros because they're not significant, although they are important. And because they're important, we're going to put a placeholder there. We're going to put times 10 to the third. It's because I started the decimal here and I moved back 3 places. That decimal doesn't really exist. You have to think about where it is. Our unit here is a gram. Our next number, notice that I have a decimal and I have a 0 after the decimal, so that number is very significant. So I have 4 important and 4 significant figures. So this would be 4 significant figures. This is not in standard scientific notation. It's times 10 to the first, so I need to move this 2 more places, 1, 2, and then I'm going to add that 2 to the 1, and this is 9.500 times 10 to the third, and then it would be milliliters. So those are your examples 1, 2, and 1, 3. So just a little more about significant figures. If I want to go through and look at significant figures in addition, probably the easiest thing to do is go through and look at your numbers. You'll notice that this one has the smallest number of digits to the right of the decimal. What I would do next is I'd first indicate that position. That's where I'm going to have to stop. And I'm going to add everything together. When I add all those numbers together, I end up with a number, and I'm going to have to flip to the next slide here. When I add those up, I end up with this number, and it's 1147.82985. But because we said that this is where we're going to stop, that is what we do in order to have the significant figure here. You can have as many numbers to the left as you want, but we can only have one to the right because we notice that that is the furthest to the right that I'm going to go. Here, this one goes a lot further, and this one goes even further. So it's the smallest number of digits after the decimal, which determines where you will have your break-off point or stopping point. That's example 1.4. For 1.5, this is multiplication. So here the product should have the same number of significant figures as the number with the smallest number of significant figures. So this one has 4 sig figs. This one only has 3. So our final answer can have 3. If you just multiply the two numbers in your calculator, you would get this larger number, or it's actually not larger than this one. It is just by a little bit. There are more digits in the number. So here I see, because I only have 3 significant figures, I'm going to have to get rid of these numbers in terms of significance, and I end up with just an answer of 109. So hopefully that's helpful. And that is significant figures and multiplication. Next thing we need to really make sure that you understand is always use units. And when appropriate, unless they tell you to use a different system of units, we're going to use the metric system. It's abbreviated System International d'Unité, abbreviated SI. It's French, and it's based on powers of 10. So it's much easier than using, there's 12 inches in a foot. 36 inches in a yard. That's a lot more difficult to do. So metric system makes everything really easy with the powers of 10. We're going to always use kgms, so kg, m, and s, kilogram for mass, m for meters, and that's for length, and then finally s is our time. You won't ever mess up the time. You might every once in a while give me inches or feet. We'll have to make sure we correct that, and then never use pounds. We're going to use kilograms when we talk about mass. Notice I didn't say weight, I did say pounds. The table here gives you all those things again. If you take 160, you'll deal with electric current, and that's measured in amperes. We will deal with kelvins. We'll talk a little bit about moles. Luminous intensity is really something that is in light, and those are some things that you'll see. Finally, derived units. These are constructed from combinations of base units. For example, if I have a kilogram times a meter over a second squared, that is really a Newton. And you'll notice that it is abbreviated with a capital N, but Newton's name, even though it's a proper noun, has a small or a lowercase n. So if I have, for example, 5 newtons, I can write it 5 newtons, or I can write it as 5 and then lowercase newtons. And that's supposed to be the standard. You won't always see that. Sometimes people will use the capital N. So basically we'll be using a lot of abbreviations. You won't ever probably write it out like that. And so we'll just use the capital N here. And this kind of goes through that uppercase, lowercase thing. And that is units. Just some common prefixes that we'll use. Very small things: femto, pico, nano, micro, milli. Centimeters, you've seen that. Don't use deci very much. And then we end up getting in bigger units. So kilo is 1,000, meg is 1,000,000, here's a billion, a trillion, and then we just keep going up from there. So just some prefixes you need to be aware of. Dimensional analysis, we're going to go through and do just an example of this. I want to convert 3.3 miles to centimeters. Whenever you start these, you always start with a factor that you're given with, so that'd be 3.3 miles. And you'd need a table to kind of tell you, or you'd have to look up how to convert one thing from the other. I know it's really easy to get on Google. You could type in how many centimeters are there in 3.3 miles and it would tell you, but on a test you won't be able to do that. Instead you'll be given some conversions. So one of the conversions that I'm going to give you here is there are 5,280 feet, and that's equal to 1 mile. So down on the bottom here, whatever I have as a unit up on top, I'm going to put a 1 here too to help us. If I have miles here, I'm also going to put miles on the bottom so that I can cross those off when I'm ready. And 1 mile, I do have 5,280 feet. Next thing I can do is say that in 1 foot, I do have 12 inches. And then another conversion that we can do is there are 2.54 centimeters, and that is equal to 1 inch. So now we're going to place my inch. I want to get rid of it. So inch goes here. 1 inch is 2.54 centimeters. At this point, I can cross off miles. I can cross off feet. Notice I'm not crossing off the numbers, just the labels. Inches, and now I'm left with centimeters. That's what I want. I like to put a double bar, kind of like an equal sign. Then that helps me go through. I'm going to put centimeters here. And at this point, we need to solve what it is. We just multiply 3.3 times 5280 times 12 times 2.54, and then divide that by 1 times 1 times 1 times 1. So 1 goes on the bottom. If you multiply on the top, you should end up with, so here you're going to end up with 531,083.52. Now, remember we talked about significant figures for a reason, and that reason is this number doesn't make a lot of sense, and we also probably want to put this in scientific notation. We started with 3.3 miles. That was the number that they gave us. Notice that we do have some other numbers here, but these we're going to treat as conversions. And because they're conversions and they're exact and they were given to us, we're going to say that they have an infinite number of significant figures. So always just use the thing that you're given. Don't worry about all these conversions when you do sig figs. I only was given 2 significant digits, so I'm only going to use 2 in my answer. You say, how am I going to do that? I'm going to have to use scientific notation. So this is going to be 5.3 times 10 to the, and then this is 1, 2, 3, 4, 5, 10 to the 5th centimeters. So now I am done with that conversion. So that's dimensional analysis and should help a little bit. General guidelines for problem solving. Whenever you solve a problem, I would encourage you to use a guess method. That would be write down anything that's given, write down the unknown, whatever you're trying to find. Find an equation, write it down, plug all the numbers in, substitute and solve, and then finally make sure that you have the correct units when you are done. So that's guess, or just a method that really will help you kind of think about how to go through and do physics problems effectively. Approximation, we freely make approximations whenever we can, and that'll turn a complex problem into a much easier one, as long as the answer will be accurate enough for what we're doing. We need to always be prepared to justify that approximation. And that really, just making sure that the answer isn't changed very much by the use of that approximation. If we think about the human body here, we could say we're trying to figure out the surface of the human body so that we can determine the heat loss by radiation in a cold room. If we think about the human body as just a cylinder, that's one approximation. So it's a pretty crude approximation. If I want to make that approximation a little bit better, what I might do is use a little bit better refined model. I might use approximations for arms, legs, the torso, and the head. And that would give us a little bit better. So that would tell us how close we are to our first estimate by just looking at the sum of those areas and then looking at that area that we did in the first part with just that single tube. We're going to spend a lot of time on graphs in class, so I'm not going to spend too much time talking about it here. And that is the end of this first lecture video.